All right, everyone. Can someone maybe tell me if you can hear me? Should be able to. Give me like a
Yep,
thumbs up
Casey,
or
we can
yeah.
hear you.
All right. Yeah, everyone coming off mute. Nice. So I will come on camera. No stress to come on camera, but appreciate everyone's time for sure. I know, sort of like hopefully I find you not working and sort of like relaxing, but we'll try to make this sort of informal as usual. I don't really do formal that well, as you can probably tell. So I thought I'd do pressure control. This is a difficult topic, I think. Certainly a difficult topic for a lot of our learners that we teach it to. It's the topic that takes the longest to get through when we teach it, and I think that it gets glossed over a lot probably. Um, and then a lot of other modes are like based on pressure control, so PRBC, ASV, um, like VC plus, autoflow, all these things are pressure control modes sort of at their core. And if you don't really understand pressure control, it can certainly set you up to like mostly torture people. So we'll try to avoid torturing people. And then sadly, this is like a one-man show, so I'm gonna have to like monitor the chat, monitor who's coming in, and then present all in one shot. So it's like pretty impressive that I can do this. All right. Who am I? I am Nick. I am Nick Gioni. Go by many monikers, Poem Toilet, aka Poem Crit, Nick Poem Crit, etc., etc. I'm from Philadelphia originally. I moved to DC for fellowship. I did fellowship in MedStar Washington Hospital Center. I did Poem Crit. Um, I do mostly crit now. I did some pulmonary at my old job, specifically teaching the vent, POCUS, sort of medical education, double chiefdom, chief resident, chief fellow, yada, yada, yada. Um, what I think makes me sort of qualified to teach this is that in the fellowship, we teach the mechanical ventilator in a specific way, sort of like this preceptorial course that started in DC and that has like sort of spread outward, and now it's kind of based out of the NIH. We have, a lot of fellowships and even attendings that are learning sort of like throughout the year. I teach the course. Um, I It's my third year as an attending, so I've been teaching it for 3 years. Um, Sort of helps me, certainly keeps me like on my toes, and I think it's important. So I sort of took to social media like before on Twitter, then sort of Twitter became Twitter, and now you sort of can't like be on Twitter anymore in some specific ways. So decided to switch platforms, and have found it like sort of refreshing that people want to learn the ventilator. So kudos for all of you guys being here. It's like really, takes a lot to come to something like this that's like very specific. I think we have a pretty good we have like a pretty good showing of disciplines, everyone from like attending physicians down to attending physicians including, I would never say down to because that's sort of pejorative, but we have multiple disciplines, attending physicians, medics, PAs, nurses, RTs, students. Um, there's people from like all over the globe. I mean, as far as like Turkey, Australia, so it's like really cool to see. Goals for this talk. So first we're going to define Ohm's law, and I promise that this will just be a little bit nitpicky, but I think it's important to go over because while we try to make things, I hate the phrase like dumb down because that sort of makes it like we're going to make the something that's really complex sound really dumb or something. And that's not what this is about. This is more about making a complex topic sort of accessible and easy to understand. So we're not going to dumb anything down. We're going to make it easy to understand. So we're define Ohm's law and what that means. The variables in pressure control, like what we set, what we measure, and then and then what are sort of like the relationship to the patient. So like what we set, what we set on the ventilator, what is the patient's characteristic, and then the interaction between the two, and then what we get and what we see, and then the physiology of pressure control. Um, Two things. One is that I'm told that the Canva sort of thing isn't really working that great. I'm going to send the slides out after in a folder like I did before, like with the recording. So no worries on that. I just sort of did them in the slides in Canva because I was like updating them throughout the day. So I just wanted you guys to have the most up-to-date ones. So as always with the ventilator, I usually start with the goals, which so like as we teach it, we teach the vent based on sort of a broad set of goals. The first are the goals of oxygenation, the goals of ventilation. So the goals of ventilation is that we want a pH of around 7.2. So we consider this something like permissive hypercapnia. Certainly in some situations we can't do permissive hypercapnia, such as right heart dysfunction, anything brain related. But in general, you can sort of tolerate some permissive hypercapnia. Remember, you can set the vent to sort of like do whatever you want. I mean, you can set it to ventilate the patient to a normal pH, but if that's at the expense of pressures and unsafe pressures, then that's sort of unacceptable. We like to keep our P plat less than 30. So this, skirts into sort of ARDS territory. We know that, rising plateau pressures are not great. Um, we were really specific about the plateau pressure in ARDS. Certainly, lower is better. So every sort of quartile lower is better. So, 25 is better than 30, 20 is better than 25, 15 is better than 20. Sometimes in ARDS, we have to sort of accept a higher plateau pressure. We like it to be less than 30 though, because we know that sort of correlates to mortality. And then no or minimal auto peep. So if you guys have sort of followed me for any length of time, you'll realize that I pay very particular attention to auto peep and um, try to avoid it at all costs. So goals of oxygenation. So SpO2 around 92%, huge moving target depending on your patient. If you're, COPD, pulmonary hypertension, ARDS, asthma, I mean, just a huge moving target. But we like to keep it around 92%. We like to keep the FiO2 less than 60%. 60% is certainly where we start to see oxygen toxicity. We have a smattering of animal and human data that tells us that if people or animals for that matter are oxygenated and ventilated with higher FiO2, approaching 100%. So if you ventilate someone with 100% FiO2, or let's say a rat, because that's how they did the study. If we ventilated rats with 100% FiO2, they would all die of ARDS in the next 48 hours because oxygen is toxic. So we like to avoid oxygen toxicity. We consider 60% as sort of like this very broad cutoff. So more than 60% we like to sort of avoid. And then adequate oxygen delivery, however you decide you're doing that. Are you checking a lactate? Are you doing a POCUS? Are you floating a swan? Whatever you decide to do, are you delivering oxygen appropriately? So I wanted to go over sort of negative pressure breathing because I think this sets us up for positive pressure breathing. Very broadly, breathing is based on Ohm's law. So Ohm's law, if we sort of claw back to our days in college and sort of physics, if we set up a differential in something, so in Ohm's law, it's sort of like a differential in for electricity. But in breathing, it'd be in differential in pressure. So if we set up a differential in pressure, you're going to have a flow based on some resistance. So if you set up a pressure differential, you'll have flow of air from higher pressure to lower pressure based on the resistance in that circuit. Okay, so very broadly. So big triangle, sort of higher pressure, smaller triangle, lower pressure. This line shows that there's air moving from the area of higher pressure to lower pressure. So sort of very simple, very basic. We like to keep it simple around here. So if we talk about negative pressure breathing, remember in your out, so even though it's not zero because it's like 760 millimeters of mercury at sea level, but as sort of for simplicity's sake, we keep it in atmosphere. So at sea level, we're at like 0 atmospheres. Okay. So in your lung, you're sort of at FRC, sort of passive expiration. So FRC is functional residual capacity. It's the size of your lung after passive expiration. You're at this sort of, a balance between the lung wanting to collapse in and the chest wall wanting to bow out. So at that, at sort of this, at this point where they sort of equilibrate, the pressure in your alveolus at end expiration is about zero. In your pleural space, so this pleural pressure is like -5. As you breathe and you drop your diaphragm, your pleural pressure goes to -8. And, you know, the concept is what's important, and these sort of specific numbers are less important. So, some say -5, some say -8, some say -10, some say -7. These numbers are not important. What's important is the concept. So, your pleural pressure drops to -8, your alveolar pressure drops to about -1. Because the pressure in your airway, sort of at your mouth, is less, or sorry, is more than the pressure in your alveolus, so 0 versus -1, air will flow from your mouth to your lungs because you dropped your diaphragm. It will do that until it delivers some volume, and then your alveolar pressure goes from -1 to 0, so flow will stop because the pressures have equalized. Then at some point you decide, I'm going to breathe out. So you stop contracting your diaphragm, whether that's sort of an active or passive process. Your lung goes back to its original size at FRC. So because of sort of this naturally passive elastic property to the lung, it's going to want to collapse downward back to this point where you get to this point where your chest wall wants to sort of bow out and your lungs wants to collapse. And because they're in contact, they sort of equilibrate at this number, which your pleural pressure is -5, then your alveolar pressure becomes 0, flow stops, and then you repeat the cycle over again. So the important concept is that to get air to move from sort of in the atmosphere, whether it's breathing normally or if you're intubated, or if the patient is intubated rather, you need to set up a pressure differential. And if you have a pressure differential, you will have flow. When you don't have a pressure differential, you will not have flow. So that's sort of the important concept to take away from this. So in positive pressure breathing, we're doing the same thing. We're setting up a pressure gradient, but in positive pressure breathing, we have a higher sort of pressure at the top. So, this applies to non-invasive positive pressure as well. So from Ohm's law, we're going to derive the equation of motion, which is the equation that governs the mechanical ventilator. It seems maybe complex, but I think when we break it down into its parts, it'll be easy to digest. And when you start to look at the ventilator from this perspective, it's a lot easier to, number one, identify normal, and number two, identify abnormal. And that's ultimately what we want to do. We want to identify abnormal by seeing normal a bunch and what we should expect to see. And then if we don't see that, we can start to diagnose like what the problem is. So based on the resistance and the compliance, when we set up a pressure differential, we're gonna get a certain tidal volume. So if we start with V equals IR, so Ohm's law, difference in something, this something happens to be pressures, equals the flow of that something, which would be air, times the resistance of something, which would be the ET tube, and then the bronchioles, or the bronchus, the bronchioles, et cetera, et cetera. So, we think classically of like asthma. If you have increased resistance, you're going to need higher pressures to ventilate. If you have AR, so ARDS is separate. That's sort of like a compliance issue, or like COPD, sort of like a compliance issue. The most pure thing would be sort of at this point at least, thinking resistance would be asthma, or let's say you intubated with someone with a very small ET tube. So like let's say a 6.0 versus an 8.0. With the 6.0, you're going to have much higher pressure to sort of deliver a volume. So if we say that that difference in pressure is like your airway pressure and your alveolar pressure, then we can substitute that for V. So in this equation, we have P airway minus P alv, so alveolar pressure, also known as plateau pressure, P alv, known as plateau pressure, equals flow times resistance. So now hold on to your knickers because we're going to move P-alv over. So now we have P-alv, or sorry, we have P airway. So the airway pressure equals flow times resistance plus P-alv. Then the question becomes, what is P-alv? So P-alv is your alveolar pressure, which is equal to the volume that you've instilled over its compliance plus the PEEP total, meaning if you set 5, but you have a total of 10 because you have 5 of auto PEEP, we have to account for that 5 in some way. So your alveolar pressure, also known as your plateau pressure, equals your volume over compliance plus your PEEP total. So if I substitute that into P-alv, I'm going to have P airway equals flow times resistance plus volume over compliance plus PEEP total. And that's the equation of motion. That's a powerful piece of information because if you think of these things in this way, sort of just algebraically, you can start to see where these patterns emerge. Okay? And I know this might seem sort of obtuse in a lot of ways, but I promise it's going to make sense. So, out of these variables, so all of these sort of equal to what we sort of set on the ventilator to deliver some volume. So in pressure control, you might have heard like this is the most comfortable mode or, whatever it is. And it's the most comfortable mode because you give the patients the most amount of freedom. And we're going to prove this right now. So for variables wise in pressure control, first, how do we make the inspiratory time 1 second? So remember in pressure controlled modes, which includes this includes things like PRVC, VC plus, autoflow. We set the inspiratory time. So you want it to be zero point 0.5 seconds, 1 second, 0.7 seconds, zero point 0.8 seconds. You're setting the inspiratory time in these modes. So one of the things that makes pressure control is that you're setting the I time. Now that might be a little confusing because on servos for volume control, you set an I time. But if you look closely, you would see that the servo spits out some flow number. Because when you set an I time and you set a volume, the servo Mackay U just figures out a flow and then tells you it. Now it's easier to set an I time, personally, I think, with volume control because you want it to be 1 second. Because before, if you saw like the old Puritan Bennett's that had like the big screens, you'd have to pick like 30, 60, 90, 120 liters per minute of flow. And 30 meant that you have like very long inspiratory time because the flow is very small. 120 meant you have a huge, sorry, 120 meant you had a very short inspiratory time because the flow was very high. But for pressure control, you're setting the I time. So 1 second, 0.8 seconds, 0.9 seconds, whatever it is. You set the I time. When you set up PRVC tomorrow or tonight, if you're working, look at what you set. You set an I time. You set a volume, but you also set an inspiratory time. One of the reasons that PRVC is a pressure controlled mode. So then, in pressure control, can we set the flow? So this is sort of the second key point, which is that you do not set the flow. So all these waveforms that I put up that are pressure control and the patient's got like some desynchrony and some people say it's flow desynchrony, increase the flow. I can't increase the flow. The flow is not fixed. It's an unfixed variable. So the patient can pull as much flow as they want. Out of the servo Mackay U, you can pull up to like 120, I think, or 160 of flow of 120 to 160 liters per minute of flow, which is like a tremendous amount. So there is no flow limitation. What limits you is the pressure in PRVC and pressure control, etc. So we don't set the flow. The flow is an unfixed variable. Okay, so the flow can be as high as the patient wants it to be. So now we set an eye time, we don't set a flow. So then what do we set? What do we set on the ventilator? What we set is the airway pressure and the PEEP. So PEEP total is in the equation, but we set the airway pressure and the PEEP. So you set the airway pressure, let's say an inspiratory pressure of, I don't know, 15 or yeah, 15, and then a PEEP of 5. So you're at a PEEP of 5. In inspiration, it goes up to 15. Your total pressure is 20. 5 plus 15 is 20. Okay. But we set those two things. So, what in this equation is determined by the patient's characteristics? The resistance and the compliance. So, resistance is, let's say you have an ET tube that's appropriate size. For, female, it's like 7.75. For a male, it's like an 8, maybe an 8.5 if you're like really feeling aggressive, which I think is kind of big. But nevertheless, I sort of default to a 7.5 for a female and an 8 for a male, unless they're like really tall, or if they have asthma. So, like an asthma exacerbation, I try to go for a bigger tube, but sort of normal, it's not 6 or 6.5 or like a 5 or something. So, resistance is really comes down to, is there bronchoconstriction for some reason? So, asthma or COPD or a mixture of two. And then the compliance. So, we sort of can't control the patient's compliance. Is their compliance low because they have pulmonary edema, or they have pneumonia, they have fibrosis? Is their compliance really high because they have emphysema? So those two things I can't control. Those are patient characteristics. So my volume will depend on the things that we set, so the airway pressures, but are also going to depend on the patient's characteristics. Now, if we're getting a small volume because of a patient characteristics, i.e., compliance, how do we get a bigger volume? We have to increase the delta. So we might have to increase our delta from a delta of 10 or 15 to a delta of 20 or 25. Now, that seems simple, but you got to remember, if we're doing that, then we're making our alveolar pressure higher, right? So all these things sort of start to interplay with each other. So things that we set, airway pressure, PEEP, things that the patient's responsible for that we're reacting to, resistance, compliance. And resistance, as long as we don't, put in like a very small ET tube. So then what's a result of the patient ventilator interaction? So the flow and the volume, which are interrelated because flow multiplied by time that we set, remember, equals a volume. So if we set a shorter time, we'll get less volume. If we set a longer time, we won't necessarily get more volume, right? Because the volume is going to be based on the patient's lung mechanics. So at some point, the pressures will equalize over some time period. And if they equalize over that time period, flow will stop and we won't get any more volume. For all of these situations that I'm talking about at this point, until I say further, we're going to assume that the patient is passive and or paralyzed. Because when we start to add patient work into it, it gets a little bit more confusing. So we'll start with just passive or paralyzed patients. So if you have a passive or paralyzed patient at some airway pressure over some time, you're going to deliver some amount of volume based on the resistance and the compliance. Based on the airway pressure, the time, the resistance, the compliance, you're going to get some volume. And then if you wait long enough, the pressures will equalize and you'll get no more volume because there's no more delta pressure. Okay? Now, this is all sort of like very um, cerebral and sort of like equations. And you're like, Nick, I mean, for real, like this is what we did. Like this is what we're doing. All these equations, like mind numbing. And I agree with you. So just like you're asleep, I am trying not to fall asleep. All right. So let's think about this for a second. So let's say Michelle thinks it helps. Thank you so much, Michelle. I'm trying not to bore everyone to death. So let's say we're in expiration and we have, so we're in expiration, okay? So we're at FRC. So we set a PEEP because we set that, remember? So we set a PEEP of 5. Remember, in expiration, the pressure in the ventilator is the PEEP that we set, and we set it at 5. Now the ventilator kicks on, and now we're starting inspiration. So we set the airway pressure, the inspiratory pressure, if you will, to 15. So remember, our total pressure is 20, but our airway pressure, inspiratory pressure is 15. We had a PEEP at 5. The total is 20. So because we set up a delta pressure, we're going to start to get flow. As we get flow and volume, we're going to start to build up this alveolar pressure because we're starting to deliver a volume. That volume exerts a pressure. So over time, we start to build volume, and because we're building volume, we're building pressure. So let's say mid-inspiration, the airway pressure is 15, the alveolar pressure is 7.5. At some point, at the end of inspiration, our airway pressure should say 20 because we have the PEEP of 15. But at some point, the pressures equalize. There's no more flow. And then when the ventilator kicks into expiration, the airway pressure goes back to 5. So this should say 20. That's my bad. Because we had the 5 of PEEP before. But hopefully you understand the concept. So we have some pressure up top. We're going to get flow until these pressures equalize. Once they equalize, there'll be no more flow. We start expiration. The airway pressure in expiration in the airway drops to 5 because that's what we set at the PEEP. Then the pressure in the alveolus is higher, so flow will now go from the alveolus to the airway pressure. Yeah, the diagram is wrong. That's my fault. So, but we will make this very clear in a second. So let's build the waveform, shall we? So let's say this is a PEEP of 5. So this red line is a PEEP of 5. Thank you, Jonathan. I appreciate that, sir. So let's say this airway pressure, so the red line is a PEEP of 5 because that's what we set, remember? So we're in expiration. Let's say the ventilator kicks on, and now we're adding from 5, which is the white line, we go up to this red line, so 15, we're adding 15, right, of inspiratory pressure. So this total pressure is 20, so you're going to see that on the ventilator. It's going to say 20. But realize that 5 of that is PEEP, and then your inspiratory pressure is 15, total of 20, okay? Now, important point number 2 or 3, I've lost count. Important point number 2 or 3 is that, remember, in the very beginning of inspiration, so at this point, remember, we haven't delivered any volume yet, right? Because we just started inspiration. So your V over C component isn't there. So your pressure here is made up from your flow, your resistance, and your PEEP total. Okay? So we have PEEP here. PEEP is 5. The ventilator kicks on for inspiration. We're adding 15 of inspiratory pressure. So now if you look at the vent, it's going to say 20 because that's the total, but 15 of that is inspiratory pressure, 5 of that is PEEP. Okay? Now, so now we set up a pressure gradient that we've talked about before. So we want to set that up so flow will move from the airway to the alveolus. So we set up a gradient. So now that we set up a gradient, you're going to start to have flow. Okay? The top of your inspiratory pressure curve is sort of like your inspiratory time. Remember, we set that. Okay? Now, this yellow line that I have in here, this is your alveolar pressure. So as you deliver flow, your alveolar pressure is going to rise because you're delivering volume. So as you deliver flow and volume, you're going to start to generate pressure in the alveolus, which is this yellow line here. So this term, the V over C, is going to start to rise. because you're delivering flow and volume. That flow and volume is exerting a pressure. So your alveolar pressure will rise as you deliver flow and volume. Because you're delivering flow and volume, your alveolar pressure is rising. That delta gets less and less and less and less and less and less and less. Then eventually it's going to equal. Then you won't have any flow. Okay? Now that's assuming that at the end, let's say this is 1 second, this inspiratory time. Let's assume that at 1 second, your airway pressure equals your alveolar pressure. So that's an assumption that we make. That's not always the case based on the patient's resistance, compliance, etc. But for example purposes now, we're going to say that at the end of 1 second, your airway pressure equals your alveolar pressure or your plateau pressure. Same thing. So as you deliver flow and volume, two things. The first is that you have the most flow and volume in the beginning because the delta pressure is the highest. As you deliver flow and volume, that delta gets less and less and less and less. Therefore, you start to deliver less and less volume and flow until you get to zero. And remember, we're assuming that because we're for the sake of the argument that I'm making. So at the end of inspiration, your alveolar pressure will go up until it meets your airway pressure. Once it meets your airway pressure here, your alveolar pressure, which is this yellow line, equals your airway pressure, which is this white line, which I've sort of put together as this red dot. Because the pressures equalize, the flow stops, so this flow goes to zero, and then you've delivered some volume based on the resistance and the compliance. Okay? So that's an important concept. That's an important concept because, as we'll see later, what we see a lot of times in PRVC all the time is that you see this airway pressure, or sorry, this flow curve kicked out, right? And then it sort of cycles off into expiration. So if the flow curve is kicked out like this, and there's still flow here, two questions. Number one, do we know what alveolar pressure is? We don't because there's still a differential. That's number one. Number two is that if I'm telling you what we call this white line is exponential decay, so you have the most air in the beginning, sorry, the most flow in the beginning because the pressure differential is the highest, and then eventually goes to zero. So the lungs are full. The lungs are full based on their properties, based on their mechanical properties. They've taken all the volume that they are able to take based on the resistance and the compliance. But if we say this purple line, which is kicked out, if we see this is the flow curve, can we assume that the lungs are taking on maybe more flow and volume than they can handle based on their mechanics? Is there something else at play that's pulling more flow into the lung, therefore more volume? That answer is yes. So, can we safely say that we know what the plateau pressure is? We can't safely say that because the patient is interacting with the ventilator to draw in more flow and volume, more than the lung sort of mechanical properties, just passively. So when we say things like, or you might have heard, in pressure control, we like pressure control because we set the volume and we set the airway pressures, and the plateau pressure cannot go above what we set. That's only true if the patient is passive and you see this flow curve get back to zero. So if you said to me, Nick, do you know what the alveolar pressure is? I would say to you, I do know what the alveolar pressure is because there's no flow. Then based on the equation of motion, I know that the airway pressure equals the alveolar pressure, also known as the plateau pressure. If there's still flow at the end of inspiration, I don't know what that is. I don't know what the alveolar pressure is. I don't know what it is. It can be higher, it could be lower. I don't know what it is. And that's dangerous because we see it all the time, especially in these adaptive modes, PRVC, VC+, ASV, et cetera, et cetera. They're targeting some number, but when you add in patient work, the algorithm can't attest for that. The algorithm can't account for that, so things start to fall off the rails. Michelle's question, and this is evidenced by the waveform. It is evidenced by the waveform, and I'm going to prove it to you. So we go back to the waveform. We have three red dots. First red dot versus the exponential decay waveform. If the patient's passive, what you should see is an exponential decay. The reason why you should see an exponential decay is because the most amount of flow and volume that you should get is in the beginning, because that's when the pressure differential is the highest. But if you have someone that's active on the ventilator, so you have someone and I have a waveform about this later, so some of this we can sort of table. But if you have, so this white line here, right? This white line here, the most amount of flow is in the beginning because that's when the pressure differential is the highest. So back to our red line, our first red dot here. If I drew a line and I got this and I did this just for this reason, I'm going to show you. So I'll try to do this on the iPad. We'll see if this works. So if I dropped a line, a red line here, all the way down, would you agree that I haven't delivered any volume? There's no volume delivered, right? But I'm an inspiration, but I haven't delivered any volume. So your pressure differential is the highest. In that split second that you've started inspiration, your airway pressure goes up to whatever you set. Your flow kicks on. So because the differential is very high, that flow is going to explode into the airway, right? So over time, as you deliver flow, your volume starts to go up. But because your volume is going up, that pressure inside the lung, which I have in sort of yellow and this beige, also starts to go up. And as you raise the pressure in the lung, that delta pressure gets less and less and less and less and less. So as your delta pressure gets less and less and less and less and less, your flow is going to go down and down and down and down and down because your pressure differential gets less and less and less and less and less. Therefore, your flow is going to go down and down and down and down and down because that differential is less over time. But if you have someone that's participating in breathing, so sort of breathing spontaneously, what they can choose to do is they can choose to drop their diaphragm and then add sort of more pressure from below. So, the vent's sort of pushing and then the patient's pulling. And remember, flow is unfixed. So, because flow is unfixed, they can pull more flow and volume than their lung mechanics allow. So, what happens is this flow curve gets kicked out, right? The flow curve gets kicked out. As it gets kicked out, all of this area under the curve that I'm sort of like highlighting in purple is extra volume that they got on top of what their lung mechanics can sort of handle based on the resistance and the compliance, which I'm going to draw in red. So if you just had someone passive on the ventilator and you saw an exponential decay in flow, the volume they would get based on their mechanics would be in red. If they're active on the ventilator, they're going to get the red, but they're also going to get the purple. So now, just to make it even more confusing, we'll make it black. So now they're getting all this volume, right? Everything that's under this curve, the area under this curve, this is all the volume they're getting. So if you said to me, Nick, what is the plateau pressure? I'd say I have no idea because they're spontaneously breathing and pulling more flow and volume than their mechanics allow. The only way that I would know or be able to sort of, figure out or tell you what the plateau pressure is by checking it by doing an inspiratory hold maneuver. Now, for my pre-hospital friends here, sadly Melody's not here because she's sort of like my pre-hospital queen, but for all my pre-hospital friends who use the T1, you can't do an inspiratory hold maneuver. It doesn't have an inspiratory hold button. So the T1 based on the resistance and the compliance, it doesn't have a button. Yep, no button. So because there's no valve or something is what Melody tells me. So because there's no button to press, there's no valve, you can't you can't get a plateau pressure. Similarly, you can't get an auto peep. So all of your values that you get on the T1 pre-hospitally are all calculated values. So two things. One is that number one, when the patient's spontaneously breathing, you cannot trust calculated values. You can't. You just can't trust them. It's just not going to work because the vent's calculating the value based on the equation of motion. So the vent sort of like knows the resistance and knows the compliance based on the volume it's giving. So it spits out a plateau pressure at you. If the patient's spontaneously breathing, especially vigorously spontaneously breathing, the plateau pressure is going to be less because as the patient breathes spontaneously, vigorously, it's going to be pulling flow from the circuit. As it pulls flow and volume, the vent's going to say to itself, wow, I don't need to pressurize as much to deliver a flow and volume. That must mean the compliance is much better. That's not what it means, right? If the patient's spontaneously breathing, especially vigorously, you cannot trust these calculated values on these ventilators. That goes for basically all of Hamilton. So if there's any Hamilton reps on here, I'm very sorry, but your ventilators more or less suck because you don't have a hold. So I don't know what the pressure is. So you don't know what it is. Now, I'm not sort of leaving you out to dry, but you need to be very cognizant when you have someone on the ventilator, especially if you're pre-hospital and using a T1 and you see this flow curve kicked out. Because when this flow curve is kicked out, that means that the patient on the is doing work and they're pulling more volume than their mechanics allow. And that's a question you need to ask yourself. If you have a patient with COPD or whatever it is, and like you're not sort of so much worried about the plateau pressure, that's one thing. If you have a patient with ARDS and you want to be very specific about the total volume they're getting, then that's something you have to consider. So, you need to look at your inhaled and exhaled volumes. If they're sort of like discordant or, you're thinking you're delivering 450 of total volume, but in fact you look at the vent and it's like 550 or something, that's something to think about because in these modes, PRVC, autoflow, all the Hamilton modes that I didn't learn the jargon for because they annoy me, but like, I don't know, like PC, CMV, all that BS. These are all pressure modes. The flow is not fixed. If the patient is breathing spontaneously, they can pull more flow. They can pull as much flow as they want than the Hamilton will allow, or whatever vent it is. Not to just rag on Hamilton. So if you're worried about the volume, you need to be very specific. APV, blah blah blah, whatever. I refuse to learn all the names. I just don't care. I don't because we're not sponsored by anyone on the Palm Toilet Instagram handle, so we can talk about all the companies sort of as much as I want because none of them are my daddy. All right, wonderful. So, equation of motion. Remember, first yellow dot, there's no VC component. We haven't delivered any volume. No volume delivered, okay? We move through, that F times R component goes down because the flow goes down, right? Because we start to the hard to see drawing in black. Thank you so much, Simran. I appreciate that. So as we move through inspiration, the F times R component goes down, and then your V over C component starts to increase because we're delivering flow and volume. Then at end inspiration, if the patient's passive, and remember, we're assuming in this situation that airway pressure equals alveolar pressure at 1 second, the alveolar pressure goes up, flow goes down. We've delivered a volume. And now your airway pressure equals your alveolar pressure. How do I know that? I know that because the flow has gone to zero. If the flow is not zero, that means that there's a differential in pressure. What that means clinically, so if the patient's like breathing very vigorously and pulling a ton of flow out, there's still a delta, right? There's still, the airway pressure is still higher than the alveolar pressure. Because they're pulling vigorously, I don't know the plateau pressure if I did a hold and checked it. And we'll show you an example of that because I think it's easier to sort of see. So I said this is pressure control one because pressure control is the most is the hardest mode to learn, I think, for our learners, certainly. And you know, not to call Simran out, but he's sort of one of my former co-fellows, and